In this video, we're going over the last in-class activity for acids and bases, so part D. So question 1 is identify the weakest acid. So the weakest acid, remember, is the one that dissociates the least. So it has to do with dissociation, not necessarily how dangerous the acid is, but how little it dissociates. So as you go down the periodic table, you have this increasing, you've got this decreasing bond strength and increasing acidity. So as you go down, the bond gets weaker and weaker. And so this causes the proton to be more and more acidic. So you have this increasing electronegativity as you go to the right. So things become more acidic as you go across, and then also as you go down. So of the answers that we have here, HF, which is at the top of the halogens, that is actually a weak acid, but everything below that is actually a strong acid. And so there's HCl, and then HBr is stronger than HCl, and then the HI is even stronger, but these are all strong acids that completely dissociate. And part of that has to do with the overlap of the bonds. So that with the HF, the size of the hydrogen and the fluorine are more similar in size. So the more similar in size, the better overlap that you can get. Whereas with the HI, you can get very little overlap because you have this really large iodine and you've got the really small proton. So you can also see that as you go down, the increase of the acidity. So it gets more and more acidic. We see this from the pKa. So the smaller and smaller the pKa, the more and more acidic that it is. So HF has a pKa of 3, HCl is -7. So we're looking at those pKa's there. So increasing acidity with decreasing pKa and increasing atomic radius. Now, something else to point out too, that HF, even though it's a weak acid, does not mean that it's not dangerous. HF is probably more dangerous than any of these others. If you get it on your skin, it can go through to the bone and can actually kill you. So if you do happen to work with HF, so it's really good for some of our geology students use it for dissolving up rocks because HF actually etches and eats away glass. So you can't store it in a glass container. So just be careful. HF is extremely dangerous. You need to know that it is dangerous if you ever work with it. And also too, you need to know how to treat HF if you accidentally get it on your skin. I think it's some kind of copper solution that you need to help counteract the effects of it. But just be careful that, remember, weak acid doesn't necessarily mean that it's not dangerous. So HF is actually really, really dangerous. And question 2, we're looking for the strongest acid. So we've got all these chlorous acids, so these chlorides and oxyacids. So we're going to show the Lewis dot structure of these acids. So here we have one oxygen, and you have the chlorine, which is very electronegative, and it's pulling electron density away from the hydrogen. Yeah, so when we're looking at all these oxyacids, so the oxygen and chlorine are very electronegative. They're pulling electron density from the hydrogen here, which polarizes this bond and making it likely that the hydrogen will leave. Well, as you add more oxygens around, the oxygens are pulling more electron density. So the more, because remember, these oxygens are very hungry for electron density. So the one with the most oxygen is going to make this proton, this hydrogen, the most acidic, because this oxygen is trying to steal electron density from this chlorine, and it's also trying to steal electron density from this hydrogen. But this chlorine has already had a lot of electron density stolen from this, by this oxygen, by this oxygen, by this oxygen. So it doesn't have as much to steal from the chlorine as it normally would. So it has to pull more from the hydrogen bond here. So it really polarizes that bond, which cleaves that bond and makes it more acidic, more likely to break that bond. And we can show this. So if we look at the pKa's of these acids, so as we increase the number of oxygens, so they're all chlorine with a central atom. You know, you've all got the proton, one proton. But as you increase the number of oxygens, it gets more and more acidic. So we go from a pKa of 7.2 down to 2, down to -1 to -10. So this perchloric acid is the most acidic proton, so that's the strongest of those acids. So the more electronegative the central atom is, the stronger the acid, because it helps weaken the OH bond. And also the more oxygens attached to that central atom, the stronger the acid. So it further weakens and polarizes the OH bond. So more oxygens generally means a higher oxidation state for that central atom. Now 3, we're looking for which of the following is a Lewis acid. So remember, Lewis acids and bases, the Lewis base is an electron pair donor. The Lewis acid is an electron pair acceptor. So we need to have some space for it to accept an electron pair. So here's the Lewis dot structure of methane, so CH4, the Lewis dot structure for the CHCl3, the BCl3, and the NH3. So these have a full octet for the chloroform as well, but the boron only has 6 valence electrons around it, so it hasn't met its octet. So it has room for it to accept 2 more electrons to get up to its octet. So we have 6. If it takes 2 more electrons, then it'll complete its octet. So this would be a Lewis acid, whereas the NH3 has a lone pair. So it has a lone pair to donate. So this would be a Lewis base. So you can almost imagine this lone pair seeing this boron that is electron deficient and being able to donate that lone pair to the boron here. So this would be a Lewis base, Lewis acid adduct. But we're looking for the Lewis acid. So that's how we're getting BCl3 for that answer. Now in question 4, which of the following is a Lewis base? So a Lewis base, remember, is an electron pair donor. So this is the Lewis dot structure for the AlF3. And then the water. So the water's got those 2 lone pairs on the central atom that can donate. And there's this C5H12, so it's a long chain hydrocarbon. And the silicon tetrafluoride. So the one that has the Lewis base that can donate electron density. So this would be the water molecule. So you've got those lone pairs on the water that can donate. Whereas the aluminum here doesn't have a complete octet, so this would be a Lewis acid. But here the water would be a Lewis base. No lone pairs here. And here the central atom has a complete octet and no lone pairs on that central atom. This is how we're getting water for that answer. Now 5, this is more of a reading question, probably not something that you would expect to see on the exam, but just something I think interesting to know and as you think about the environment. But when you think about acid rain and marble statues, so the reason why the acid rain can eat away the marble statues with the acid rain is because the marble is actually composed of calcium carbonate. So there's just a little reading question. So like also think about if you ever have any marble countertops, be careful, because make sure you always keep those countertops sealed, because if you lose that sealant over the marble countertops, if you're getting kind of acid like soda, or if you get some kind of acidic juice on there, it can actually eat away part of the countertop and discolor it. But marble countertops are really great, transfer heat really well, and nice, smooth, really great for baking pastries and rolling out cookies and pie crust and things like that. Now in 6, they want us to determine the pH, and they've given us the concentration of an acid solution. So this carbonic acid, they tell us the diprotic acid, and we've got the first Ka for the first acid coming off. So remember, this is a really small number, so not many of those protons are going to come off. And then the second number, this is the second proton that comes off, the Ka for that. So this is a much smaller number. So remember, these are orders of magnitudes difference. So for the most part, we can ignore that second acid dissociation. In your upper division classes, when you get to revisit the equilibriums, then we'll have you deal with both of those Ks. But for right now, for us, we're just going to, because this is such a small dissociation amount, that it's not going to matter with the sig figs. So just to kind of show you, so the carbonic acid, we treat it just like any other weak acid. So we're starting off with the initial concentration of 0.18 for the carbonic acid, 0 for the H+, 0 for the bicarbonate. So minus X plus X plus X, products over reactants. And I did the approximation. And if you multiply both sides by the 0.18, take the square root, X will give you 2.7 times 10 to the minus 4th. And if you do the check here, the approximation is valid. But remember, this X is the proton concentration. So negative log of the X, you get 3.5 and 3.56. So this is the pH of that solution. So this is how we're getting D for number 6. Now, if you wanted to just double check, just to prove that that second dissociation isn't going to make a difference. So here is the second dissociation. So I'm starting off with that concentration from the previous slide. So the second dissociation, so we're taking that bicarbonate to the carbonate ion, so minus X plus X plus X. This initial concentration of the H plus is from the first dissociation that it's created, so that we have the initial H plus concentration here, but the carbonate is 0. But we're still doing the minus X plus X plus X, plugging this in, and we're doing an approximation again, but solving for X. So X is 5.5 times 10 to the minus 11. So that's a teeny, tiny, tiny number. So if you add this to this number, yeah, it doesn't even make a difference with a sig fig. So we're just showing you that it was okay for us to ignore the second acid dissociation, and we still get a pH of 3.56 when taking the sig figs. Okay, if you have questions, make sure you ask during class or come see me during office hours, and I'll be glad to help.